Good evening, students.
Good evening, ma'am.
Um, so after I started the syllabus, I found two more topics to be covered in Unit 2. So I would be starting with it. After I finish that, I would be, uh, you know, any doubts in yesterday's topics? So we are continuing the chapter of file system implementation. And the first topic in that is directory implementation. We looked at directory, files, partitions, file system, on disk structures, in memory structures, and so on. Moving ahead, we will look at directory implementation, how to implement a directory. And there are two ways to implement a directory. First one is linear list. Second one is hash table.
Add your screen, ma'am.
Screen is not shared.
Yes, ma'am.
Oh, sorry.
Okay, ma'am.
Right.
Thank
So directory implementation, linear list and hash table. What is a linear list implementation of directory? It implements a directory as a linear list containing file names and pointers to the data blocks. We know there are blocks on the disk that contains the files. Here, this is our directory. This is the directory structure. This directory structure is implemented in the form of um, linear list. Here you will find file names and here you will find pointers. These pointers point to the data blocks. These are the data blocks of file. Suppose if the file name is F1 and this is F1, the data block belonging to F1, this pointer would be pointing like this. If there is another file, say F3, and this data block belongs to F3, then the pointer would be pointing here. We know that yesterday we saw we have folders or directories. Inside directories, you will have files. How actually are these implemented in operating system, in file system? That is what we are discussing now. So the first method is linear list. The advantage of linear list is that it is quite simple to program. You know, you have just one list wherein you insert all the file names, and wherever they are, you know, in the on the disk, they would be having some data blocks related to those files, and they have the addresses. Those addresses are stored here at this point, you know, in pointer, and this is like traversing the directory structure. The advantage is simple to implement. However, the disadvantage is that you need to perform the linear search one by one. Linear list means linear search. Uh, Linear search, you start with first, you go to second, you go next, third, and so on until n. This is linear searching, or performing operation linearly. If you perform operation randomly, you can jump directly to this particular file number 3. This direct jumping is not possible in linear list. It supports only linear search to find a file. You have to start here, and then you have to traverse, and then you have to find the pointer, and then you have to, enter to that data block of that point. The next one is hash table. Second implementation of directory is a hash table. Hash table has a hash table. You know, it also leverage this linear list. It has this. This is hash table. This is linear list, and these are our data blocks. All right, these are data blocks. And then linear list has file name and pointer, means the address to the data block. And here, if you observe here in hash table, you will have a value stored here, which is computed from the file name. If you have a file name f1, you apply some operation on this file name to obtain the hash value. If the hash value of f1 is 5, then here at location 5, if you start with 1, 1, 2, 3, 4, 5, at this location you will find f1, uh, which is nothing but, actually this is the not f1, this is the value, hash value of f1. And then pointer will point to the file. Say f1 is here, and here this is the data block. So what are you doing? You are randomly finding a file. How are you finding the file randomly? By applying an operation which is known as hash operation on file name to obtain a hash value. And by using the hash value, you for this hash value, you directly get the uh, file name, pointer to the file name, where you can directly get the address of the data block belonging to this file name. Does it make sense? If not, you can ask anytime, you can interrupt me and ask. And the advantage of using hash table is that it obviously decreases the directory search time. You don't have to traverse linearly. You just apply a hash function on a file name, obtain hash value, provide the hash value, feed the hash value in the hash table, and then for that hash value contains the corresponding file name's address in the linear list, and from there you can um, get that data block address. All right. The next one, going ahead, the next topic is allocation methods. What are the allocation methods to allocate space to the files you have on the disk? Blocks. In what manner the blocks are allocated to the files? That is allocation methods. Let me give you an analogy. If there are in a classroom like this, if there are 10 benches, okay, and here 10 students arrive, okay, these are 10 students, and this is our classroom. And in this classroom, we have 10 chairs. How these students will sit on these chairs? Is there any policy or any strategy? Is it like all girls sit this row and all boys sit this side? Or is it based on their marks? The topper will sit in the front, or the least performer will sit in the front. Different methods you can have, but typically it's random. Whoever comes in the class first, they occupy their place. But as an analogy, try to understand that there is some space here and there are some students, and then you have to allocate this space to the students. Likewise, you have space on the disk. On the disk, you have space in the form of blocks. This is divided into sectors are divided into blocks, and here there are blocks. And now the question that arises is how to allocate space to the file, on disk. So if a user creates a file f1 and it has got uh, if you consider that each block takes 1 MB, suppose, uh, and this F1 requires 16 blocks, then which block is to be allocated to F1? This first block, and you proceed in that direction, and and then you might have these block already occupied. There are chances that first three are free and then fourth one is occupied. Then what you have to do? For that, there are three methods. The first method is um, this is allocation methods, continuous allocation. Second method is linked allocation. Third method is indexed allocation. These are the three methods that are followed in order. Excuse me, students. Sorry, students. So, mm, going ahead with the continuous allocation. In the continuous allocation, each file is allocated set of contiguous blocks on the disk. For instance, consider that you have this disk, and disk has the blocks, and then there is a directory structure. That directory structure has to keep track of all the files that are residing in that directory. So in this directory structure, we have file name, and then you have starting address, and you have the length. Length means the number of blocks that that file requires. And in contiguous allocation, file gets the sequence and series of blocks contiguously, means one after the other. Consider F1. F1, the length required for F1 is 3. And if I say that uh, this one is already occupied, this one is occupied, then if I start allocating the space for F1 from block number 3, and the length is 3. So F1, F1, F1. Continuously, you are allocating 3 blocks to F1. And what is the starting block number? It is 3. All right. This is contiguous allocation. The advantage is the number of disk seek is minimum. Because if you start reading the file in one read, you can get the entire file because it is sequentially stored, and due to that the performance improves, and eventually accessing the file turns out to be easy. On
Ma'am,
the
I have one question.
Yeah, please go ahead.
Ma'am, in the same scenario, what you are explaining in this file, length is 3, and then the start is at the third position. But
Mhm.
in the disk, we have only first two has been allocated already to some other file, and then second, third is available, and third one is allocated. Let's say, then
Mhm.
how the allocation is?
Yeah, we'll come to that. We'll have second method. That's why we will have linked allocation.
Oh, I
Because
see.
of that, the drawback which you just stated, if there are no sufficient blocks available contiguously, what to do in that case, right? So contiguous allocation will fail in that case, because it is essential to have sequence of blocks available. Only then you can allocate the space to a file, okay, in contiguous allocation. The disadvantage is finding space for a new file is quite difficult because of the problem of having continuous blocks. Here this is a trivial example in which the length is 3. Consider a file having length of 1000 or 2000, and suppose there are no 1000 blocks available contiguously, then this contiguous allocation cannot be implemented. And also a major problem is external fragmentation. The fragmentation arises because now these three has been allocated to F1, and suppose you are allocating this one to F5. Consider F5 has this 4, and then this F1 has 2. No, F2. F2 has 2 blocks. Like this, what happens? You go on allocating, and then once you delete a file, if you delete this file F1, then you see that these 3 blocks are here, which are free, which might not be allocated to other files if the other files do not have the same length. So then these 3 blocks remain empty. That's a major problem, and you need to determine in advance what is the length of the file. If you know what is the length of the file, only then you can allocate the space. If you don't know, you can't. So you need to determine in advance. These, um, although contiguous allocation is simple and easy, but it brings lot of disadvantages on the table. So we are going to the next method, which is linked allocation. In linked allocation, each file consists of linked list of data blocks. Linked list, if you know linked list, it has two parts. Linked list has two parts. The first one stores the value, and second one store the address, which is a pointer to the next block. So you have this next second node. This is first node, this is second node, and they may not be in sequence. You can have first node or block at one place and second at other place, because you are storing the address as well. It's not like sequentially you are accessing, you are storing the address. That's why linked allocation contains two parts. One is having the value, second one is having the pointer to the next block. If you just consider this example here, I have like this blocks, and the directory structure. This is the directory structure. It has again 3 columns: file name, start means starting address, and ending address. If you observe here, you don't have length, rather you have ending address, because when you start allocating, you also uh, go on storing the address of the next block. This block is F1. This is F1. All right. Then this one is next F1 block. And then this one is next F1 block. And then this one is next F1 block. All right. So F1 starting is 1, ending is this one. 1, 2, 3, 8. Block number 8. Starting is block number 1, ending is block number 8. And this way they are keeping track of the next block. And then there is no need to have continuous. Let's suppose these are already occupied. Here you can have F2, and then you can have a pointer to the next block. The advantage is that there is no external fragmentation. Wherever there is a block, you can just use it and have its address in its preceding block and store the address of the succeeding block. It's that simple. And the address, the size of the file need not be known in advance. You need not determine what is the file size. Even if file expands or shrinks, it's quite easy to handle here, because if it expands somewhere here, you allocate here, it might be this one F1, and then create a pointer. All right. The disadvantage is that this one is effective for sequential access, not for random access. You see that directly you cannot jump onto this part of F1. In order to jump onto this part, you need to um, traverse, starting with the block number 1. You start with block 1, go to block 3, and then from block 3 you need to go to 6, block number 6. Your desirable block is 6. Directly you can't go it. And another problem is if there is any failure in this chain. If here there is a loss of this pointer, then there is a break, in the file, and then it's not possible to access the rest of the file if there is a break in the chain. All right. And then because of these problems, in order to effectively implement this, a variation came in, uh, was developed. It was known as FAT, file allocation table. This file allocation table is a variation of linked allocation method, and in FAT, file allocation table, a section of disk contains the table, which is this table, FAT table, and this table has one entry for each disk block indexed by the block number, and then it is like this. This is our FAT, file allocation table, and here it has all the um, one entry for each disk blocks. This is block number 1, 2, 3, 4, 5, and block number 1 has a pointer to block number 3, and 3 has a pointer to block number 6. Like that, in order not to lose this pointer address, you create another table called fat, and then you keep track of this addresses. And then the directory structure includes the file name and then the starting block number. Starting, if the file name is f1 and starting block number is 1, if you go here to 1, here you will find the address 3, means that is the next block. Then 3, at 3 you find the address of uh, 6, the next block. Like this you proceed. All right. Next, this one, third one, indexed allocation. The third method, indexed allocation, it uses an index block that contains all the pointers. All right. And then what happens is, if this is our disk and these are our blocks, these, besides having these data blocks, you designate some of the blocks to be index blocks. If you have this block as index block, then if f1 has if f1 has been allocated block number 1, 2, and then 3, and then 6, and then 8, if there are 4 blocks allocated to f1, then here you will find 2 comma 3, 6, and 8. So this index blocks contains the data block addresses, and then once you read the first block, you get to know that again you can read the second block. Likewise you can proceed. uh, the advantage of this is that it supports direct access, right? If you want to directly access block number 6, because all the blocks numbers have been listed out here in the index block, you can jump anywhere, you can access anywhere. You don't have to sequentially follow like 2, 3, 6. It is not strictly mentioned that you have to follow this. You can directly access first block number 6. And it also does not suffer from the problem of external fragmentation, uh, as it can use blocks anywhere available on the disk. The disadvantage here is that, um, can anyone tell me the disadvantage? The disadvantage is it
It will,
requires. Yeah, yeah. Please go ahead.
if we directly access block 6, then if we want
Hmm.
to go to block 8, then we need to go back to the block 2, I think. Then only we can get the address of the another next following. Is that the disadvantage?
Um, Again, you don't have to. Why do you have to go to block 2? Rather, you have to go to block 1, because 1 is the
Yeah, yeah.
index block, right?
Yes, yes. We need to go back to the
One,
main
uh,
one index.
main, right? Okay, that is one. You need to refer to index block every time to get to know the block data block numbers. Then you have to have separate data besides having data blocks, you have to have separate index blocks, and that is like an overhead, space overhead. If out of if you have consider that there are 100 data blocks, actually there are 100 total blocks. Out of 100 blocks, if there are 10 files, if there are 10 files, then you need 10 index blocks, so you are getting only 90 data blocks. 10 files, for 10 different files you need different index blocks. All right, this is for those files whose data block numbers can fit in one index block. In case you can't fit all the data block numbers in one index block, perhaps you have to have more index blocks for each file. if a file is very large. Okay, if out of these 10 files, if 6 files are too large and their index values cannot be stored in one index block, then probably you might be using 3 blocks per file. So 3 into 6 is 18 blocks plus 4 blocks. So total 22 blocks you are using only for index, storing indexes. This much overhead associated with this indexed allocation. And another question that arises here is, in case each file has multiple index blocks, how to store these index blocks, whether they have to be stored contiguously or linked through linked structure or through multi-level structure. So how are you going to store index blocks of each file when they are more than one in number? All right, that is another issue that need to be addressed in case of this. So you can go for linked scheme, means having uh, addresses of index blocks in subsequent uh, blocks. You have to have address as well of the next block in this chain of index blocks. Here you can have, this is also, consider that this is also an index block, consider that this is also an index block, this is linked structure. Or you can go for multi-level index. Multi-level index, you have first index that contains the addresses of all index blocks, all right, which further contains the addresses of the data blocks. Or you can combine the structure, uh, combined structure where combined you are using this approach in which you have first level blocks, data blocks, you have second level data blocks, in the sense that this is pointer to, direct pointer to data block, this is pointer to the index which further has pointer to data block. Then you can have pointers to indexes which further has pointer to indexes. This is two level. We can combine this multi-level approach in this format, okay, for storing index blocks. Okay, and then this one here, you need to also have a, here this is um, index allocation and directory structure. For index allocation, we'll have file name and uh, pointer to index block. So file name F1, pointer to index block 1. So if you go to 1, you will get the pointers to data blocks. Then the next, you have any doubts?
Yeah, madam. Can I know the
Hmm?
difference between the fat and then the linked structure? So what is the difference there? I didn't understand. Is this fat
All
and then
right.
the top one, above one?
Yeah, yeah. Yeah, sure. Here, the address of the next block is stored within this block. This is block number 1. This is block number 3. Here you see 3 is mentioned, right? And here you have 6 stored. So instead of having like this, 1 storing the address of 3, 3 storing the address of 6, in fact, you create another structure, a table. Say that on this disk you have fat. Okay, this fat itself is one structure. that structure will contain this one. Block number 1 will have 3, and then block number 3 will have 6. So here in this block you don't have the address of the subsequent block, rather you have in a separate structure known as fat. Here you will have just the data part, okay, and then you will, to get the address you need to go to fat. Here you have the starting number, block number. So f1 starting is 1. Once you enter in this block number 1, in this fat structure you get the next block's address. Here you need to, this is the actual block, data block, okay. In this block only you are storing the address of the next data block. Here you have separately stored, okay. If I have to give you an analogy, if you are writing operating system notes, and you require 3 notebooks, okay, to write. In the first notebook you finish perhaps 2 units, and the last page, these notebooks have been given the numbers, notebook number 1, 2 and 3. On top, on the first page you paste the notebook numbers, okay. And this first notebook on the last page will have the say that because notebook was 2 was not available, you have started writing in 3, okay. It is like you have started with notebook 1, and then you continued your notes in notebook 3, and after in notebook 3 last page will contain the address which is 2, okay. So this is the first notebook, this is the second, and this is the third. This contains 2 units, this contains 2 units, and this contains 1 unit. If this is the case, this is this linked allocation. Fat allocation means what? You maintain a diary. In this diary, what you do is, for OS, unit 1 and 2 are in notebook 1, and 3 and 4 are in notebook 3, and unit 5 is in notebook 2. Like this you are writing in this. So you don't have to go to the last page of this notebook to find out which is the next note. You just open your diary. Perhaps in this diary you store other subjects information as well, for DBMS, for EIT, and for all the other papers also you maintain information in this diary. You just open the diary, find out, go there, take the notebook, and then this way, this is linked allocation and this is having fat. Does it make sense?
Yes,
Did
madam.
it
Yeah, thanks.
clarify? It clarifies your doubt?
Yes, madam. Thanks.
Okay. So next one is this free space management. Free space management is about how to keep track of the block that have been allocated and that are free. Here, if this is your disk, these are the blocks, and consider that these are allocated, and these in blue color without cross mark, they are free. All right. So here you need to have at some place the information about all the free blocks. If you have the information, it would be easy for you to uh, know, determine how many blocks are free. All right. So for that purpose, there are different techniques. First one is bit vector. Bit vector is like you maintain a vector, and here for every indexed by block number, For every block number, you have an entry. If block number is free, perhaps you may use 1. No, these two are 0 0. This is 1, this is 1, this is 0, and so on. You can read out. You can read when you read in the sense that if you just retrieve how many ones are there in this vector, you'll get to know how many free blocks are available. And then linked list. Linked list, again same. Here this free block will have a pointer to the next free block. This free block will have a pointer to the subsequent one, and then this continues. And third one is grouping. What happens is all the free blocks uh, addresses are read, and then they are stored in the first free block. So here we have 3 4 6 8. 3 4 6 8. You might store, actually you might go for if they are continuous, then you can write here in the first block you can write 3 and 4 are free, or you can have like all the addresses 3 4 6 8, all three here in this first block, and you store the address of first block, first free block. You uh, read the first free block to determine all the addresses of free blocks. That is grouping. Third one is counting. Counting is here what are you doing? You are storing the addresses. Instead of storing the addresses, we can store the count. Okay, this block followed by one free block, that is the count. And in case consider this, here all 5 are free, all 6 are free. So here you can write this is free, and 5 free blocks followed this free block, so you can write 5 here. That is counting. Okay, and then efficiency and performance. So what you can do is in order to improve the efficiency, you can go for different mechanism in advance, pre-allocating inodes on the partitions, and then you can directly um, read you can get to read you know at a faster rate, so you can speed up the task. This is all about the remaining topics of unit 2 under file system implementation topic. And any doubts in this?
No, ma'am.
Okay, fine. So I would be starting now unit 3.
Madam, one question.
Yes, yes,
On
please
the
go ahead.
file allocation, right? You have specified the 4 types of allocation, like the contiguous and fat and linked and
Mhm.
other one. So, which is the best, madam, out of these all currently? Which one we are using?
In Unix, we use this combine approach. This one. What is this known as combined scheme, in which you have this in inode itself you store this. There are actually in this 15 pointers. Okay, in these 15 pointers, first 12 are allocated for direct addresses. Next, one level, two level, three level. Okay, so this is being used in Unix, and the same kind of structure is being used in other operating system, where you can't fix it. You can't have only one single approach to serve the purpose. That's why you are using here a sort of combined approach. Okay, and contiguous one, it cannot be used at all. Continuous approach you cannot use. Linked
Yeah.
also cannot be used. And what are you doing here? Here you are using linked. This is only linked approach has a problem. So you are using this inode. This is one separate structure. In this structure, you have pointers to data blocks. These are like direct pointers. Here there is no link, nothing involved. When for 12 point, such 12 pointers are available, followed by the next one, which is having the single level approach, wherein pointer stores the address of the linked list. That list contains the addresses of data blocks. If a file grows, if a file does not grow, then these are adequate. When the file started growing, you can go for this next level. If further it grows more, then you can go for next level. Like that, you can proceed in this manner. Does it clarify your doubt?
Yeah, man. Yes.
Okay.
Thanks.
Um, next one. Next one is uh, Unit 3. I'll be starting Unit 3 in that process synchronization. Actually, I referred to your syllabus yesterday to found out
Yes, ma'am.
that those topics were missed. And then, so PGDCS syllabus, operating system. Here, so the last here, you see file system interface implementation is done. This one is recovery in case of system crash or any problem in the disk. There is a recovery manager that keeps a log file. In case it fails, then it records and you can restore later. Or you can also do backup by yourself manually. So that recovery is about it is concerned with how to get the data in case of any failure. Okay, so now I'll be starting process synchronization.
Okay, ma'am.
Before beginning the actual technical topic, let me give you an analogy. When siblings share the room, okay, if there is a room and there are two siblings sharing the room, okay, consider that there are two sisters who are sharing this room. Then what happens is they are um accessing or using different resources that are there in the room, right? You may have a study table. If there are no two study tables, then they have to share the same study table. Perhaps they have to share the wardrobe, and few other things they have to share. They might have few things exclusively for them and few things they have to share. They may sometimes what happens is that both of them would like to use a particular resource at the same time. When they have their own resources, it's not at all a problem. They have their own study tables. Most of the time, they may not have. So only one study table they have to share. And when they have to share, here suppose if you have a chair, only one sister can sit and another one also want to sit and read or do something, then the conflict arises. All right, when conflict arises, when something has to be shared, and when two processes, or here in this case these two sisters, when they start looking for the same thing at the same time and using it. Now in a computer system you have multiple processes, and there are processes which can share the logical address space. If two or more processes, process 1 and process 2, they share same logical address space, they mean same address space. When they share address space, they might be trying to concurrently access a shared resource. All right, so what happens is, if there is a data in this program, here there is x, this x, um, to in order to perform a write operation on x, only one process should be allowed. If both start writing, then it leads to inconsistent value to x. Only one should write at a time. But suppose at the same time both would want to modify this x value, then uh, here also the conflict arises, and then this kind of situation where there is a resource in the form of a variable or a table or a file which is shared among n processes, n number of processes, and then uh, all of them or few of them try to access this at the same time, then this critical section problem, process synchronization problem arises. Okay, you have to somehow create a synchronization among them so that they cannot create any conflict or inconsistent state for the shared resource. Consider an example of producer and consumer. There is a problem actually. This is a problem known as producer consumer problem. In this producer consumer problem, there is a process which produces a value, generates something. Okay, a process called producer generates or produces, and consumer, another process, consumer, known as consumer, absorbs it. Okay, takes it, consumes it, and then what happens is, uh, consider this situation that producer producer is producing, means increasing the value of x from x to plus 1, whatever is the value of x, that it is increasing to plus 1. And consumer, after it consumes, it has to reduce, right? So x should be equal to x minus 1. We know that modern operating systems perform interleaving of uh, concurrent execution. When these statements are interleaved, then what happens at time t naught? producer will execute in its register. It initializes its register to a value X. When a program is in execution, certain registers are assigned to programmers to store the values, the intermediate results. So essentially what is happening here, you are storing, producer is storing X value into a register. And what consumer is doing, consumer is also storing X value in its register. Okay. Uh, at time t1, okay, like this parallel it will not work. I have to, this action is performed by producer, and then at time t1 this is performed by consumer. At time t2 consider x is having a value of 5. So here this is being performed by producer. Then producer's register value is equal to 5, and at time t1 producer is saying register 1 is equals to register 1 plus 1. This is also done by producer. And then what is the register 1 value, register 1 belonging to producer? Okay, it will be 6. At time t2 consumer says register 2 is equals to X. So consumer's register 2 is equal to 5, right? Still, if you observe here, changes are not reflected. Still they are in registers. Once you save, then only this variable gets the updated value. Here saving has not done yet. While execution, there is an interleaving. Interleaving means what happens? Context switch happens. Some part of producer is executed, then there is a switch to consumer process. The part of consumer process is executed, and there is a switch back to producer process, and this one continues. At time t3, consumer says register 2 equal to register 2 minus 1. So consumer's register 2 is having a value 4. All right. At time t4, if producer says X is equals to register 1, and at time t5, if this producer says, if consumer says X is equals to register 2. Now here it is 6, here it is 4. If you observe here, both the values are wrong. If you done this sequentially, if you perform producer task first, what is the operation producer is performing? Increment. So X will become from 5 to 6. Then if consumer performs the operation, it will get 6 value, not 5. So 6 minus 1 is 5. Eventually the outcome should be 5. If consumer says 5, reads first. This is producer reading first. If consumer reads 5 X value before producer, 5 becomes 4, and then producer has to read 4 and add 1, which becomes 5. In case of producer before consumer, outcome is 5. In case consumer is executing before producer, outcome is 5. And when they are performing concurrent execution, or interleaving of execution, the outcome may be either 6 or 4, depending on which one is executed. If T4 is executed first, outcome is 6. If T5 is executed first, outcome is 4. So this is the problem which I'm talking about. When two or more processes try to access a shared resource and try to modify, and it leads to inconsistent value. And this kind of situation is known as a race condition. What is the race condition? If producer wins, value is 6. If consumer wins, value is 4. There is a race being made between the two, and whoever wins will give us a wrong result. And to avoid this race condition, what we have to ensure that only one process access a shared resource at a time, and for the purpose of manipulation or writing. Another analogy is, earlier we had this PCO centers. Even now, presently, we can go for ATM centers. In this, you can have only one person using. Here also, you can have only one person. If there is only one machine, there should be only one person. Second one have to wait outside. Here also, second one had to wait outside. If he or she enters, and if they both start fighting for this receiver of the phone, then they may end up breaking it. And here also, they may end up losing their PIN and other confidential information. There are situations wherein only one process has to access the resource at a time, like here. So moving on with critical section problem, you might have understood by now that there is a section of code which is critical. Why it is critical? Because it may lead to inconsistent state. Therefore, this critical section means a part of the code where there is a writing being done should be made available only to one process at a time. Um, so when one process is executing in its critical section, okay, because processes are sharing their address space. I already mentioned it that when one sister here is there on this seat, okay, another has to wait until this one finishes. When one process is executing, this is a critical section, this part, this segment of the code. Consider that this segment of the code is critical. You can have uh, parts of the program or the code that can be simultaneously accessed by processes. There are things that can be simultaneously accessed. For instance, if there is a big bed, both the sisters can use it without any conflict, without any problem. But in a scenario where only one can use, otherwise there is a problem. So that kind of scenario demand that only one process should be in its critical executing in its critical section. When other process tries to execute in its critical section, it has to wait. And each process have to request permission to enter its critical state. And that section of code Okay, here this is process P1, this is process P2. There is a critical, because they are sharing. This is critical section. Only one can enter at one time. So you have an entry section, you have this critical section, and then you have this exit section. You have entry section, critical section, exit section. Once a process P1 checks in the entry section that critical section is not being executed by any other process, it can enter inside. Okay, and then this is like it is entering inside the critical section. At the same time, if this process P2 checks its entry section, because already another process is in its critical section, this has to wait. This cannot enter. This is P1 and P2. These are cooperating processes sharing the address space. All right. Next, there are solutions that have been proposed, and these solutions to critical section problem must satisfy three requirements. There are three requirements for the solution to CSP. Satisfy three requirements. Three requirements. So what are the three requirements? First one is mutual exclusion. First one, mutual exclusion. Second one, progress. Third one, bounded waiting. Mutual exclusion means that only one process is allowed to execute in its critical section. That is mutually exclusive. It cannot be shared. Progress, when one process is trying to enter its critical section, the decision, uh, whether to allow it to enter its critical section is made by those processes that are willing to enter the critical section, not the other processes. Okay, all those processes uh, participate in the decision about who should enter in its critical section. It's like sort of queue. Okay, so they are in queue, and then one by one they come out of the queue and access the critical section, and everyone should be given the opportunity to access. Everyone should proceed. It's not that one process is indefinitely waiting to enter its critical section, whereas other processes are entering, exiting, again entering, and so on. So apparently here uh, everyone should be given the opportunity to enter, to execute, and to exit. Bounded waiting, uh, after a process requests to enter the critical section, there should be some limited time, uh, after which it is actually given the access. The time should be, bounded. It is not like it is waiting indefinitely and not getting uh, that access, and then waiting and waiting. It should not be like that. After say two processes, it gets to enter in the critical section, or after 4 process, or even after 10 process, but it has to get, whenever its turn is there, it should enter. That is this. There are several solutions proposed, presented for this critical section problem. Uh, the basic solutions are known as two process solution. This two process solution is mainly to deal with the situation in which there are only two processes and which share critical section. So what happens is it is like turn system here. You use a variable, say t. If t is I, pi will enter. If t is j, pj will enter. And then this is like alternately they have to do. If pi is entering first, then pj will enter. After pj, pi will enter. After pi, pj will enter. It's like that. Or you can have another situation where they may use some flag. In flag, they have a value of 2. If flag 1 is true, it means p1 is in critical section. If flag 2 is true, it means that pj is in critical section. P is the process, I and j subscripts are the different process. So pi and pj are two different processes, and they are trying to somehow come to a point wherein they both agree, when who to enter next. And then you may have a combination of both the flag and turn, and then you may have, that is about two-way, two process solution. You can have multiple process solutions. In multiple process solution, what happens is there are n processes. It's not just pi and pj. And in this, the solution is that whenever a process enters, uh, try to enter the critical section, it is being given the id, a number, and whichever process is having the least number will be allowed to enter the next. It's like token system in when you go to a bakery or a restaurant. When you get a token, if your token is 1, in if other person token is 2, uh, 1 will be served first before 2. So whoever is having the token number value lesser will get the service before. So like that, here each process is given a number, and whichever process is having the least value will get the opportunity to enter. And then next one is another important and successful technique for this critical section problem is semaphore. Semaphore is an integer variable. Okay, semaphore s. This is an integer variable. So integer variable, you know that it can take values like 0, 1, 2, 3, 4, 5, 6. And then you can perform operations like initialize. You can initialize this variable, mutex variable. You can also call this as mutex, or a semaphore variable, a semaphore. You can initialize, you can perform wait operation on this semaphore. You can perform signal operation on this semaphore. Uh, how it works is that, consider that there are two processes, and P2. This is the critical section of P1. This is the critical section of P2. And this is our variable semaphore S. Semaphore, generally is initialized to a value 0 or 1. And suppose if semaphore value is 1, if semaphore value is 1, it means that there is no process executing in its critical section. All right. So what happens? P1 checks up the value of semaphore. When it checks the value of semaphore, it finds that it is 1. Because it is 1, what P1 does is, P1 makes it 0 and enter its critical section. So now it is executing in its critical section. When it is executing in critical section, at the same time, P2 tries to check the value of semaphore to find whether it is 1 or 0. Because it is 0, what P2 does is, P2 calls operation wait on this semaphore. On this semaphore, P2 is calling an operation wait. Now P1 is executing and then has reached the end of the critical section, and then what P1 does is, okay, this is wait, let me draw another. So this is S. Now it is 0 because P1 is in its critical section, and P2 is willing to enter its critical section, and P2 is waiting because P1 is in its critical section. What P1 does is, after it finishes the execution, it send a signal. It sends a signal to semaphore S that changes 0 to 1. And because P2 is waiting, P2 can enter it. Because P2 is waiting on S, so P2 now can enter its critical section. Is it clear? This is how they synchronize. They ensure that only one process is executing in its critical section through the use of an integer variable known as a semaphore. And this semaphore, you can initialize it to 1 initially, and then you can perform an operation of wait and signal. The uses of semaphore is actually are, there are primarily two uses. One is mutual, it ensures mutual exclusion, and also it ensures this process synchronization. Okay, process synchronization means synchronization of processes. It performs both the tasks. It addresses synchronization problem and mutual exclusion problem. So what is mutual exclusion? Ensuring that only one is executing. What is synchronization problem? Both should coordinate, okay, and execute one after the other serially. All right, they should coordinate and execute serially. So semaphore is used for both the tasks. If you observe here, it is indeed supporting mutual exclusion, because when P1 has entered its critical section, by making it 0, P2 is waiting. So it is mutually exclusive. Only one can be in its critical section at a time. And it addresses synchronization problem among processes. Here P1 P2 is executing after P1. This is like serial execution. Some things have to be executed serially, not concurrently. So that serial execution is happening here because of semaphore. And then there are different primarily two ways to implement semaphore implementation. Semaphore implementation can be done using busy waiting method or using queue waiting. Uh, in this scenario, what P2 does, uh, please
Wait.
wait a minute. Yeah, anything to ask?
No, no.
Okay. Here, when one process P1 is executing in its critical section, there is a semaphore S. There is another process P2, and here S is associated with P1 right now. So what P2 does is P2 keeps on checking S value, semaphore value, whether it has turned out to be 1. It checks after one, consider, I'm saying 1 minute, it's not 1 minute, rather not even 1 second. It's, repeatedly, say every 1 second it is checking P2. After 1 second, again after 1 second, again after 1 second. So this is known as busy waiting, and also known as a spin lock, in which a CPU cycles gets wasted. Why it wastes CPU cycle? Because P2 checks the status of semaphore, that also requires processor to perform some operation. So this is known as a spin lock, and it wastes CPU cycles. To overcome this problem, this is busy waiting. To overcome this problem, another method is to have P1 executing in its critical section and P2 just execute wait once and does not invoke this semaphore again and again. When P1 finishes, it sends signal which informs P2 that P1 has finished, has done with its critical section. You can enter. So this is not continuously checking. It is, if I take an analogy, uh, you 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 would like to know from when you have your exams. Every day, morning and evening. Hmm? Every day, morning 9 a.m. and then evening 5 p.m. You might be checking website. Okay, you as a student check the website again and again every day, 2 times, to know whether the timetable has been released or not. This is one way, which is this busy waiting, which wastes your time. Another method is your institution itself will send a message, email, WhatsApp message to inform you that uh, the exams are going to begin. This way, it is like you are getting a signal. You are not checking again and again. You have registered for the course, and then you get it. You don't have to do anything. So that this is this one, queue waiting. And then when they are in queue, it's not only about P1 and P2. P2 is waiting, then P3 might also try to access semaphore and check whether it can enter. Likewise, when semaphore is 0, it becomes -1, and it may become -2. And then this number shows that how many processes are waiting in the queue. And the one which is at the front will be getting the signal first, and then uh, using the semaphore to access the critical section. It's not about only two processes, it's for n processes. And you have two kinds of semaphores. You just now what I showed you is a binary semaphore, and you have counting semaphore. In binary semaphore, you have a value only 0 and 1. In this counting semaphore, you can have counting semaphore has a value which will be like 1, 2, 3, 4. Binary can take only 0, 1. All right. Types of semaphores. Then there are the problems, classical problems, which are solved by this semaphore. The classical problems of synchronization, which are first one, producer consumer problem. Second one, readers writers problem. Third one, dining philosophers problem. Consider first, producer consumer problem. In this, there is a pool of n buffers, and each buffer can hold an item. Okay, and the mutex semaphore, this mutex semaphore will provide mutual exclusion for access to the buffer pool. So it is like this. You have a buffer pool, okay, memory buffer, which means memory. Hmm. In this memory, you can write and read, and there is a producer and there is a consumer. What this semaphore does? How does semaphore solves this producer consumer problem? If producer is using or accessing this memory, then semaphore value will be 0, and then this consumer, what consumer does is consumer has to wait. So let me, this is producer and this is consumer. What producer does? Producer will wait until the memory buffer becomes empty, and then um, wait on this mutex variable m. And this is critical section. What is critical section? This one, adding. This is entry section. And what is exit section? This signal. Signal m mutex variable and signal full. What consumer does? This is exit section. Consumer, because consumer is waiting for what? Waiting for the memory to become full. Whenever there is, whenever this happens, whenever it becomes full, there is a signal. When producer adds all the elements to this memory, producer will send a signal that now memory is full. When memory gets full, consumer starts uh, taking that, reading that, or consuming that. And consumer wait on a mutex variable. Why mutex variable is required? Because of to ensure mutual exclusion in the sense that no other process should enter when it is removing. What consumer is doing? Remove the item. This will add the item. This will remove the item from this memory. And then after removing all the items, it send a signal on mutex, means now others can access. And also it send a signal that it is empty. What is empty? The memory is empty now because producer is waiting on empty. Producer is waiting for the memory to get empty. When consumer says signal empty, there is a signal sent. This is sent to producer. When producer receives empty signal, what producer will do? Go to this next wait. Might be any other consumer is there or another process is there. It wants to check. If there is no one, it gets even M signal. For instance, from here, it gets M signal uh, to enter the critical section. Then it enters, add the items. Like this, uh, Semaphore gives the solution to producer consumer problem. And then there is a readers writers problem. Second one, readers writers problem. In this reader writer problem, uh, there are few processes which are interested in reading a file or a record, and they are known as readers. The processes, those who are interested in reading, are known as readers. And there are processes that are interested in updating or modifying, and therefore they are known as writers. So essentially what happens in reader writer problem is that, consider this, there are readers, there are writers. These readers would like to read and writers would like to update. Here, if two or more readers access this file or any other resource, shared resource, there are no adverse effects that will result because of shared access, because all of them are reading. Now, I'll give you an analogy here. There are teachers, there are students. Teachers are teaching, students are listening. If there are two teachers teaching at simultaneously, then what happens? These students will not understand anything because their both of their voices will overlap, and then you get some mixed type of information that is nothing but a chaos. You can't understand anything. This teacher is like this writer, so there should be only one writer, there should be only one teacher. When teacher is teaching, no other teacher should enter, like that. And there are students, you can see that you can have a number of students. You cannot and need not put any restriction on the number of students, because having n number of students does not create any problem. They all are just listening. You can have 10, you can have 100, as that does not make a difference. So like that, you can have multiple readers reading, and whenever this writer starts writing, no other process, no reader or writer should be allowed to access the critical section. And that solution is given by this semaphore in this manner. So what happens is there is a reader. This reader process will wait on M, which is nothing but the mutex. Mutex will ensure mutual exclusion. And then there is a read count. Why? What is the need of read count? To determine how many readers are there. Once another reader join, this count will be incremented. And if read count, hmm, if read count is 0, no, if read count is 1, then wait. Writer has to wait. WRT. And you have to signal M, and then you can perform reading. Here reading operation is being performed. This is a section which can be read and which can be written. And after reading is done, wait on mutex. Why to wait on mutex? To decrement the read count. Count minus minus. Here count plus plus. After a process finishes its reading, it has to decrement the value because it is exiting now. So count read count minus minus. If read count turns out to be 0, then at that time you can signal write process, because there are no readers now. When there are no readers, only then writing can be done. And signal M, mutex, means now that other process, writer process, can enter. What is writer? What is writer doing? Here writer is waiting on WRT, means this is also semaphore. This WRT is also semaphore, M is also semaphore. You can have any name given to that semaphore. The primary purpose is to ensure this mutual exclusion and avoid synchronization problem. And here writing is performed. After writing is performed, it just gives signal. So here what happens when reader is waiting, and if it gets the signal M, it increments the count. And if count is 1, count is 1 means it is the first process. When it is the first process, it waits on WRT. Waits on WRT means what? It waits until the writer finishes writing. After that, it signal to writer uh, M, that is mutex. Why it is signaling? Why it is signaling? Because multiple writers can enter here. Sorry, multiple readers can enter here, but writer cannot enter. So writer has to wait. M is for other readers. Mutex is for other readers. So other readers can enter here. So it is signaling that, okay, next another reader process R2. R2 will wait on M. If it gets a signal, it increments the count. And then if because it is the second one, this will not be 1. So directly it can signal another reader and start reading. Another reader is waiting here. When it gets the signal, it increments read count, and then no need of executing these 2 lines and signal another reader and reading. So now in this situation there are 3 readers reading. All right, after that what it does, it waits so that another reader gives signal to decrement the count. If it gets M, it decrements the count. Means now what? The third reader has gone out. Then like this, second reader can go out and third reader can go out. So when the last one is there, after last one decrements, it gets to zero. Read count becomes zero. Then it signals wait. No, write. Then it send a signal to write, WRT. Then this writer can start writing because it is waiting for WRT, and then it can write and it can give signal. Once it finishes writing, when it gives signal, this reader will know. When it gives signal on WRT, here this signal will go to the first reader. Okay, if the reader is the first one, then reader is waiting for this signal after a writer finishes writing. This is the way in which Semaphore solves reader writer's problem. I think we should stop now. The dining philosopher's problem and the rest of the other topics we will continue tomorrow. Any doubts so far?
No, it's okay, clear, understood. Little bit confusion, but yeah, Semaphore is more clear and made it clear on the other topics. So actually, ma'am, I
They
have
are
one
clear?
question. Yeah, yeah. One thing I want to know is
Yeah.
that, ma'am, this kind of questions will come in the exam. We need to mention these all types of process synchronizations. We need to give
Yes,
this so
they
many
are very
details.
important. Yeah, if suppose you get a question like explain producer consumer problem and how Semaphore addresses it, then first you have to write what is a producer consumer problem and how Semaphore address it, and that whatever I wrote, no, that
Hmm.
section of code for producer, section of code for consumer, that wait on empty, wait on mutex, add, or that
Okay.
that you have to write, and then you have to explain that you need to
Got it.
learn those
Okay.
things.
Okay. Okay, madam.
Okay,
Understood. Yeah.
and
Thanks.
these are actually quite important because these are classical problems of synchronization addressed by Semaphore quite well. So
Hmm.
you have to learn producer consumer, readers writers, and dining philosophers.
Okay.
Okay, two have been covered today. You please go through, and also I will share, I will post the video. You can go through it once again, and then tomorrow I will continue with the dining philosopher's problem.
Sure, madam.
Okay, then see you. Bye.
Thank you.
Thanks, madam. Bye.
Bye.